Poisson bracket and equation of motion. Here we are going to deal with the Poisson bracket in terms of Jacobian determinant. Jacobian determinant. Now we know that the Poisson bracket f comma g, also let's write f comma g, that's equal to dou f by dou q into dou g by dou p minus dou f by dou p into dou g by dou q. So this we can write as in the form of matrix or the determinant as this one, dou f by dou q, and here we have dou f by dou p, and this is dou g by dou q, dou g by dou p. So this is the Jacobian determinant, and this is how you write. The numerator should have the same function along the rows, and along the down the rows, column, you have same function as dou q remains the same, or dou p. Okay, yeah, so that means the denominator is same in the column and numerator is same in the rows. Now as for example, q can be written as P inverse in terms of the momentum, that is this capital Q here, and this, and here capital P. This is a function of QP squared. Now let's write what is the Jacobian determinant here. Dou by dou q of capital Q and dou by dou p of capital Q, and here we have the dou p by dou q, here we have dou p by dou p. So this is the Jacobian, and now let us write down the derivative here. With respect to q, you are differentiating this, so which is ultimately 0, and dou q by dou p, that is with respect to p, you will get dou q, so that is 1 by p minus 1 by p squared, so minus 1 divided by p square, dou p by dou q, 2qp, so it's 2qp, and dou p by dou p is it's p squared, and it's 2pq. Now determinant is this minus here, So 0 minus uh, p square times minus 1 by p squared, that's equal to 1. So the Poisson bracket gives the value 1. So this is an example how we can write the Poisson bracket in terms of the Jacobian determinant. Canonical transformation. So another beautiful concept, canonical transformation. Now if we have a system with Q and P and it's moving to another system with QP, what does it happen? So how we can move from one system to the another? So that is done through transformation called canonical transformation. And let's understand that Q, which is a function of Q comma P, is moving to Q comma P, and capital P, which is again a function of P of Q comma P. So this is what we know. And the Poisson bracket of QP on small q small p gives you the Jacobian determinant in this way, that is dou q by dou q, that is capital Q, and dou capital Q by dou p by dou q, and this is dou p capital P by dou p. So this is the Jacobian for the Poisson bracket of Q comma P. And here we must also remember that the transformation is from this 1 to 2, that is represent 1 and 2, and also you can transform it from 2 to 1, that is capital Q to capital Q capital P to small q and small p, and again the transformation is back. So such transformation occurs so that we have the conservation of certain quantities. Okay, now QP as a function of small q and small p. Thus we can also write the Poisson bracket of Q comma P, which will be again function of capital P and capital Q, or Q capital Q and capital P, which means that it is Q which is function of capital Q and capital P, comma P is also function of capital Q and capital P. So again the Jacobian can be written in the form of dou Q by dou capital Q, and here we have dou Q by dou capital P, and dou P by dou capital Q, and dou P by dou capital P. So this is the Jacobian for the transformation from 2 to 1. Now assume there is a transformation from this is Q, this is P, and here is a point and small area here, and this is being transformed to another coordinates that are Q, and this is P, and now here we have another area which is given by, this area is given by dq dp, which is equal to dA. There is small change in area, and now here we have dA dash, which is equal to dq dp. Okay, now the relation between dA is and dA dash is, that is dA dash is equal to some constant j times dA. So that is dA dash equal to some constant times dA, and what this constant is nothing but the Jacobian. So the Jacobian times the initial area as the final area in the another system. Now we can write the Jacobian as equal to dA dash by dA, which is equal to dq dp by dq dp. Now this is nothing but dou q or q comma p by dou of q comma. Now that's fine. Now let us find out as an example how we can move forward. Now assume that there is xy coordinates. So here we have y, this is x, and the small area is nothing but dx dy. Now here on the another system we have r and theta. So what is this area is all about? And this area, so this is dx dy, so we can write dr d theta, but we know that this is not equal to dr d theta. Whatever here we have here, dx dy is not equal to dr d theta, so we have to assume that there is a transformation from x comma y to r comma theta. Okay, so the transformation from x comma y to r comma theta, we can write dx dy as equal to j times dr d theta. Now dou of x comma y divided by dou of r comma theta. Now that's equal to dou x by dou r, and it is dou x by dou theta and dou y by dou r and dou y by dou theta. So this is the Jacobian we need to get. So we have to write x and y in terms of r and theta. So here x is equal to r cos theta and y is equal to r sin theta. Now x equal to r cos theta and x equal to r sin theta. Dou x by dou r, dou x by dou theta, dou y by dou r, and dou y by dou theta. This is what we need to find. So the Jacobian becomes So dou x by dou r, so cos theta, and dou x by dou theta, so theta is here, so r sin theta with a minus sign, minus r sin theta. Now dou y by dou r, that is sin theta, and dou y by dou theta is r cos theta. Now it's r cos square theta plus r sin square theta, so that is equal to r cos square theta plus r sin square theta. Now that's equal to 1. Sorry, that's equal to r. So Jacobian for this is r. Now let us see whether it matches with the concept that we have just learned, that is dx dy equal to j times dr d theta. Now what is j? J is equal to r, so that's equal to r dr d theta. So now we know that this is the small change in area in plane polar coordinates, right? So as a practice work, I request you to work on this. The transformation is from xyz coordinates to r theta phi, that is from Cartesian to spherical polar coordinates. Spherical polar coordinates system. Now the question is to find the Jacobian. To also find Jacobian for the transformation from x to that means the Cartesian to spherical polar coordinates. So far we were dealing with transformations from one coordinates, say for example q and p, q of small q small p and p of small q small p. So transformation is from capital Q capital P to and from small p qp. So this was the transformation, and the transformation is said to be canonical. The transformation is said to be canonical if the Jacobian is equal to 1. So which means the Poisson bracket of q comma p on qp, that is q comma on qp is equal to 1, and Jacobian is equal to 1. So which means that the determinant dou q by dou q by dou p by dou q by dou p is equal to 1. So this is how when a transformation becomes canonical, that is the Jacobian has to be 1 or the Poisson bracket has to be equal to 1. So when we say that dA dash equal to j times dA here dA dash will be equal to dA. So this is what happens in Jacobian. And in Jacobian transformation, both the initial system and the final system have same area and same volume, which means area and volume are preserved. And this implies that the Hamilton's equation of equations remain same. This implies, this is the final conclusion, Hamilton equations remain same. Here we have a problem. For the transformation, from Q equal to minus P square by 2 and P is equal to P to the power m Q to the power n is canonical. Then values of m and n are. So this is a question. So we have Q, P moving to P, Q and P. So this gives us the determinant. If you want to find out whether it is canonical, you have to find out the Jacobian first. Dou Q by dou Q, dou Q by dou P, dou P by dou Q, dou P by dou P. Now, so that's equal to dou Q by dou Q. So that's with respect to Q, differentiate this, so that's 0, and with respect to P you have to differentiate Q, so minus P, so it's minus P here. Okay, now dou P by dou Q, which is equal to m to the power n, P to the power m, Q to the power n minus 1, and here we have m, P to the power m minus 1, Q to the power n. So this is the determinant. Now this gives us 0 minus, that is this, so 0 into minus n P to the power m Q to the power n minus 1 into P equal to, so the determinant has to be equal to 1, minus and minus, so this becomes plus. So n P to the power m Q to the power n minus 1 into P. So n Q to the power n minus 1 and P to the power m plus 1 is equal to 1. So this 1 can be written as P to the power 0, Q to the power 0. So n minus 1 equal to 0 and m plus 1 equal to 0. This together has to be equal to 0, which implies n equal to 1 and m equal to minus 1. So for m equal to 1 and m equal to minus 1, the transformation is canonical. Here we have capital Q is equal to 2p plus 3q, and capital P is equal to p by 2 plus alpha times q. Now the question is to find alpha if p comma q transformation is canonical. Applying the Jacobian dou q by dou q, dou q by dou p by dou q, and dou p by dou p is equal to 1. So we have, what is dou q by dou q? That is 3. Dou q by dou p is 2. Dou p by dou q is alpha, and dou p by dou p is 1 by 2. So now we need, this is equal to 1. So 3 times half, that is 3 by 2 minus 2 alpha is equal to 1, which gives us 1 by 2 equal to 2 times alpha, and this gives alpha equal to 1 by 4. So when alpha equal to 1 by 4, the transformation is canonical. Another question. So this is, as a practice work, please continue this work. That is q is equal to q plus 4ap, and p is equal to q plus 2p. This is question number 1. Find, this is the find a if the transformation is canonical, and the second question is q is small q, is not the capital one. So root of 2 alpha p sine q, and p small p is equal to root of 2 alpha p cos q. Now here we need to find out the transformation or the Poisson bracket. Q comma p equal to 1. So the transformation changes, the it becomes dou q by dou q, dou q by dou p, capital P, and this is capital P, this is also capital P, this is also capital P. Okay, so dou p by dou q and dou p by dou capital P. This should be equal to. So here you need to find out alpha. So find alpha if the transformation is canonical. Here we have a question. The question is, capital Q is equal to q to the power alpha sine of beta p, that is small letter p, beta p, and capital P is equal to q to the power alpha cos of beta p. Now the question is to find alpha and beta. Find alpha and beta if the transformation is canonical. So the QP equal to 1 gives dou Q by dou Q, dou Q by dou P, dou P by dou Q, dou P by dou P. So we need to find out the Jacobian. So that gives us, let's write down here. So with respect to Q, we have to differentiate Q. So this becomes alpha Q to the power alpha minus 1 into sine of beta P, and this is with respect to P. So you have Q power alpha, instead of sine we have cos beta P and multiplied by beta. Now again dou P by dou Q, that is again alpha Q to the power alpha minus 1 cos beta P. Here it is Q to the power alpha cos, with you have a minus sign, so sine beta P times beta. So this determinant should give us 1. So multiplying the diagonals, that is alpha alpha times Q to the power 2 alpha plus 2 alpha minus 1 into beta sine square beta P, sine square beta P. Again you have, so this is minus, again you have minus, so alpha Q to the power 2 alpha minus 1 cos square beta P times beta, so here we have not beta, equal to 1. So 1 you can write it as Q to the power 0, P to the power 0. Now Q to the power alpha minus 1 is 0, so 2 alpha minus 1 gives us 0, and and here alpha into beta should be equal to 1. So that means here you have again minus, so minus of alpha beta should be equal to 1. So 2 alpha minus 1 equal to 0 implies alpha equal to 1 by 2, and so minus of 1 by 2 times beta equal to 1, and beta equal to minus 2. So alpha equal to half, beta equal to minus 2. So this is where, now why here this is minus sign, this is minus sign is because here we have one minus and this minus. So minus of these quantities inside should be equal to 1. Only then you will have q to the power 0 alpha p to the power 0 will be equal to 1. Here we are trying to understand the canonical transformation, the point transformation, and the gauge transformation. Now canonical transformation, now let us understand that there is a transformation occurring from qi pi to capital QI capital PI, and this transformation is canonical. This transformation is canonical. So this is a canonical transformation, and in this transformation let us understand the Lagrangian, Hamiltonian, and specifically the equations. So Lagrangian in the first chord system is function of q dot and t, while in the another transformation, and after transformation it becomes L dash, which is a function of L dash of capital Q dot and T. Similarly Hamiltonian is the function of Qi, Pi and T, that is everything small. H dash is equal to Hamiltonian is a function of Q, P and T, or you can write Qi, Pi, and Hamiltonian from Lagrangian we can arrive at sum over Qi dot Pi minus L, and Lagrangian is equal to sum over Qi dot Pi minus H. Similarly here we have H dash equal to sum over capital Qi dot capital Pi minus L dash, this is sum over I. Similarly L is equal to sum over I Qi dot Pi minus H. So this is L dash, this is H dash. Now the equations, Qi dot is equal to dou H by dou Pi. Similarly Pi dot is equal to minus dou H by dou Q, and Qi dot equal to dou H dash by dou p I and pi dot is equal to minus dou h by dou k. So these are the equations. Now here we have a theorem which says that Lagrangian is invariant under the addition of total time derivative of a function. That is, Lagrangian is invariant means it means that Lagrangian may change. Or it changes, but the equation of motion remains same. This is what is meant by invariance of Lagrangian. Equation of motion remains same. Okay, so according to the theorem, L dash, that is the new Lagrangian, is equal to L plus or minus df by dt. So we are adding a function which is total time derivative, and this is called, f is called gauge function. Gauge function or generating function. We will represent it by GF. So this generating function, when you add the total time derivative of this generating function, we would get the Lagrangian would change, but even if it changes, the Lagrangian equation of motion does not change. As an example, we can start with Lagrangian equal to half x dot square minus half kx square. So this is the Lagrangian that we have, and the equation of motion says that d by dt of dou L by dou x dot minus dou L by dou x equal to 0. This says that dou L by dou x dot is nothing but x dot, so x double dot, that is plus kx, dou L by dou x is kx, and minus of minus becomes plus, so x double dot plus kx equal to 0. So this is the equation of motion. Now once we have this equation of motion, now what we are going to do is we are going to add some total time derivative of some function. That is, let me find d by dt of beta x square. So beta x square is the function, so its derivative will be equal to 2 beta x x dot. So 2 beta x x dot. If we are adding this particular thing to the Lagrangian, let us see what happens. So Lagrangian is equal to half x dot square minus half kx square plus 2 beta x x dot, then dou L by dou x dot is equal to x dot plus 2 beta x, then d by dt of dou L by dou x dot is equal to x double dot plus 2 beta x dot. Okay, now we need to find dou L by dou x, which is equal to 2 kx plus 2 beta x dot, so 2 beta x dot. Now equation of motion is d by dt of dou L by dou x dot minus dou L by dou x dot. So this is the first term, this is the second term. When we subtract 1 minus 2, you would get, there is x double dot here, 2 beta x dot and minus 2 beta x dot will get cancelled. So equation of motion again remains the same, that is x double dot plus kx equal to 0. So even though the Lagrangian is changed, see, Lagrangian has changed, half x dot square, we have added this particular term. So even though this term is being added, the equation of motion remains same. So this is called gauge function or generating function, which is being added. So what is the gauge function? Gauge function will be the integration of whatever we are going to add.